another invited talk from Ashish Choudhury. He is based right now in the National University of Singapore, but I do believe he happens to be in Cambridge, of all places, right now on an internship with Bell Labs. So it's great to have you here today, and great to see that you're physically close to where I am, and we can meet up later on. So thank you so much for joining us today and sharing your work. Let me first ask. So how do you pronounce the system name? Is it RETEXO, or I don't know how you would say it?
It's it's called RETEXO, Nick. RETEXO.
RETEXO.
Yeah.
Okay, it's a really cool name. Okay, so then your work is all about how do you train neural networks over these distributed graphs and so on.
This work is about that. My thesis is also on this, but also doing it more privately, like including things like differential privacy and stuff.
Fantastic. Well, this seems to be right up our alley. So I'm going to stop sharing and allow you to take over and tell us all about it. I remember I met you last time. Last time I saw you physically was at the Flower Summit.
Oh yeah. I attended the summit. It was great. It was a great experience.
Okay, amazing.
I mean, meeting all of you guys, working. We all have similar interests, so it was nice to meet a lot of people who I was able to talk to with similar interests. People could understand my work and then give me feedback. It was pretty good.
Oh yeah, there's definitely a huge value in having like a concentrated community that always shares a common vision. So yeah, cool. I'm really excited to see your work.
Can you see this?
Yep, looks good.
Hello everyone, I'm Ashish, and thank you for the introduction, Nick. It was a great introduction. So I don't have too much to say apart from, I'm a PhD student currently with NUS, in NUS. I'm a final year PhD student. Today I'm going to talk about how to efficiently train neural networks over distributed graphs. So a brief introduction to my research trajectory. So I've worked in the past on many things. I've worked on blockchains, and my work in blockchains has been pretty popular in the past. It has created some news as well. I had a lot of fun working on blockchains. And then I worked on program debugging and synthesis, and I had several good works in that. And I also won like a best paper award, like my work won best paper award at one of these conferences. And my whole thesis work is on trustworthy federated learning. It's not on the previous topics. And this, I'm looking to design like federated learning algorithms for graphs, heavily distributed graphs, and I also want to keep them trustworthy, which means like having nice things like privacy and robustness. So today I'm going to talk about one of those works. Okay. So before going deep into the work, I just want to give you a flash of like how was Flower useful for this work. So typically, when you want to train a graph neural network on a graph, so you do it in the centralized setup. So let's say there's an attributed graph, you train a graph neural network, and then you learn representations for each node in the graph. But let's say you distribute the graph, especially you fully distribute the graph where each client holds just a single node. So here a client is a mobile device. And then you have, if there are n nodes in a graph, you have n devices, and then they communicate with each other, right? So if you have such a graph, then if you want to train a neural network, a graph neural network in a federated learning fashion, then it's basically impractical. I'll show you why, but it's impractical. So you can't train a GNN. So what we do is, we introduce our work RETEXO, which creates a different version of graph neural network called RETEXO GNN. And RETEXO GNNs, which are implemented on Flower, on top of Flower. So RETEXO plus Flower, we create RETEXO GNNs, which are practical to train in the federated setup. And that means we can do the applications, we can basically implement the applications, we can satisfy the applications for which graph neural networks are used. So it looks like this. So there's a Flower server, and then there are Flower clients. So the beauty of federated learning over distributed graphs is that you have two kinds of communication channels. There's client to server communication channel, and then there's a client to client communication channel. Unlike other federated, like typical federated learning setups, where there's only client to server federated learning, client to server communication channels. So Flower provides client to server communication channels, but in order to do this federated learning over graphs, we also create client to client communication channels. We extend Flower to have this as well, this functionality as well. So yeah, eventually by adding a little bit of functionality to Flower framework, we are able to train the first GNNs for fully distributed graphs. Okay, so let's go to the details of the work. So machine learning over graphs is very important for many applications. For instance, social network analysis, recommender systems, anomaly detection, and the list could just go on. And graph neural networks are state of the art in this field. They have been already implemented and deployed in production at several companies. So the graph neural networks are layered architectures where you have many aggregation layers and classification layers, and they're interspersed with graph adjacency matrices. This all looks very complicated, but let's simplify this. So typically, graph neural networks are used to find representations of nodes. So let's say here we want to find the representation of node A. So the way this happens is that, so let's say you have a graph neural network with two aggregation layers, AGG1 and AGG2. So to find the representation for A asks its neighbors to give their representations, intermediate representations, coming from aggregation layer 1. So here in this graph, A's neighbors are C and D and B. So it just asks them for intermediate representations. And then because C and D and B need representations from their neighbors to pass through aggregation layer 1, they ask their neighbors, okay, give me your features. And then once they get the representations from their neighbors, they pass it through aggregation layer 1, and then they have intermediate representations which they give it to node A, which can be passed through aggregation layer 2 to get the final representation. So basically this is GNNs propagate the representations over the edges of the graph, and this is called message propagation or feature propagation. So this way you can aggregate information over the graph. So there are two kinds of setups, essentially, one a centralized and two a distributed setup. So in the centralized setup, you have the graph over, so in the centralized setup, you have the node features and the edges in the same place, and GNNs have been designed for this setup. So in this case, the message propagation happens locally, whereas in the distributed setup, there are clients, and each client stores a subgraph or a partition of the graph, and then there's a server which doesn't know the graph. So the clients basically do not want to or do not share the graph with each other. So in this setup, you need some sort of collaborative learning or federated learning procedure to learn a GNN. And as I said, learning a GNN would require message propagation, but in this case, the message propagation would require communication among the clients because there'll be inter-client edges. So why do we care about distributed graphs? Distributed graphs are everywhere. So for instance, you might have at an organization level geopolitically restricted social networks or financial networks where like you have a part of the graph in some country and you cannot share that data with some other country. Or at an individual level, you can have like a network of personal devices or sensors. So think of it as like a contact tracing kind of an application which the governments have done in the past few years. So like you have a huge network of connected individuals and they're meeting each other, and they carry their mobile phones everywhere, and the edges are formed from proximity channels. And the applications there are like classifying the users based on that, based on the features that they store on their phones and the people they meet. So just to summarize federated learning in this regime, so you have like a centralized setup where essentially there's no federated learning. The graph is there in the centralized servers, and then you train a GNN. And then you have a cross-siloed setup where there are a few clients storing massive subgraphs, and you conduct federated learning. Here there's client-to-client communication, but at a smaller scale, only for inter-client edges. And then you have a cross-device setting where like you take it to the extreme, and there's the devices are the clients, users' personal devices are the clients, and each client holds information about just one user or one node of the graph. So there's a fully distributed setup. So in this case, if you want to do federated learning, every client has to communicate with its neighbors, and there's a huge communication overhead. So as you can see, as decentralization increases, the privacy increases, right? In the sense that the data is stored more and more on clients' personal devices, closer to the client, but then the communication complexity also increases. So our overarching problem statement is how to train GNNs communication efficiently on distributed graphs. However, we focus on fully distributed graphs. Why? Because fully distributed graphs is the worst case. It has the best privacy and the worst communication complexity. So if we can come up with a solution for this, we can extend this to other federated setups as well. So in a fully distributed setup, just to remind you, each client stores only information about one single node and its edges. So if you want to do federated learning, the clients have to share gradients with the server, and there's a common assumption. And we also have two more constraints, and this is specific to graph learning, which is the clients will have to communicate with each other over client-to-client communication channels. And clients will have to share some sort of intermediate representations with their neighbors, and only then the graph learning would be possible. So this is very different from typical federated learning. This is very new. Okay. So to give you a flavor of how GNNs could be trained on fully distributed setup, let's just look at how it might work. So let's say the server sends the GNN to the client, and then the client will have to do a local training step. To do that, it has to do message passing. And in a fully distributed setup, if it has to do message passing, it will have to ask all of its neighbors over the network for intermediate representations. This is a very hard thing to do. And on top of it, you would have to do the gradient computation as well. So training GNNs is basically impractical to do in this kind of a setup, because first of all, you have message passing for every federated learning round. So in every federated learning round, the client has to communicate with its neighbors, and they have to communicate with their neighbors as well, depending on the size of the GNN. So we did a simple simulation, and we found that even to train a 2-layer GNN for end-to-end would require each client to send over 6 to 64 GB of data over the network, depending on what kind of client it is. And gradient computation has to happen over the network as well. This is very different from typical gradient computation, because here the individual clients do not have the full computation graph to compute the gradient. So it has to ask its neighbors for certain factors to compute the gradient. This is a very hard problem by itself. And finally, as it's very common in mobile networks, they could be asynchronous. So if you include that factor as well, then it basically becomes impractical to train GNNs. So we have come down to a place where it's like I'm just saying it's very impractical, but in this work we actually give a practical way to train something like GNNs on fully distributed graphs. So we come up with a novel transformation of GNNs called RETEXO GNNs that can be efficiently trained on fully distributed graphs with a small performance loss. Because RETEXO GNNs require very few message passing rounds. They do not require each one message passing round for every federated learning round. Instead, they just require k message passing rounds if it's a k-layer GNN. And k could be like as small as 2 or 3. And then because of that, it has very low data transfer volume. It could be like an order of magnitude lesser than like training a GNN. And even on client-to-client communication channels, it requires very little data sharing. And also, because of the way it is designed, the gradients need not be computed over the network. You don't need the network to compute the gradients. They can be computed locally, which is very easy to do, and we all know how to do it. And already federated learning platforms implement this. And finally, we show that RETEXO GNNs are practical for deployment in mobile networks. And we demonstrate it with the FLAR framework as well. So to understand RETEXO, we need to understand why GNNs require so many message passing rounds. And as I mentioned, every forward pass would require message passing on the network for a GNN to train a GNN. But that's a very high level argument, right? If you think a bit deeper, the reason why we need so many message passing rounds is because of this optimization objective. So the optimization objective for a typical GNN roughly looks like this. So you have to optimize aggregation layer 1 and aggregation layer 2 with respect to the input and output and a loss function. And the thing is, the key observation here is that we have to optimize all the layers simultaneously. Because this is the optimization objective, we have to do this message passing over the network. So this is the key observation. Now let's use this observation to create something different. So our key idea is to use an age-old technique called sequential optimization. It's basically a greedy optimization technique. So what we do is we investigate how to sequentially optimize layers of a GNN based on a local optimization objective. So instead of optimizing all the layers together, we do it one at a time. And we give a novel way to do it for graphs. So it's quite intuitive and simple. So what we do is, so let's say we have a 2-layer GNN. So for a moment, forget that there's an aggregation layer 2. So let's just take aggregation layer 1. And then append a classifying layer on top of it. So now a local optimizer becomes this. What is the optimal aggregation layer 1 that can minimize this loss function? So basically, we try to just pass the features to the aggregation layer 1, and then do classification just based on that, and and then optimize over it. So if we do this, then all A needs to do is just ask features from C, D, and B and store them locally, and then train this aggregation layer. So it doesn't have to do this multiple times. So it just has to do message passing once. So this is just training aggregation layer 1, and this aggregation layer 1 captures information, like it learns how to aggregate information from the 1-hop neighborhood of the graph, forgetting about the 2-hop neighborhood. And then we also need to include information from the 2-hop neighborhood, right? So for that, what we do is once we fix the aggregation layer 1, we pass the features through the aggregation layer 1, get some intermediate representations, which are optimal for the local objective. And then we use that to train the aggregation layer 2. So the optimization function just becomes training aggregation layer 2 based on the conditional inputs that it gets from the trained aggregation layer 1. So in this case, we still need just one message passing round because A just has to ask the intermediate representations from C, D, and B once. And then because it has the aggregation layer 2 locally, it can keep training the aggregation layer 2 locally based on intermediate representations from C, D, and B. So this is the entire idea of sequential optimization of GNNs. and RETEXO GNNs. So at a high level, RETEXO looks like this. So let's say this is a GNN. You can take any GNN. It has two aggregation layers. Then apply RETEXO on it. It's a framework. So you can take any GNN and apply RETEXO on it. So first, it'll create one model which will learn from just the inputs. It doesn't have any aggregation layers. And then it'll use the intermediate representations from the inputs to train another model which stores the first aggregation layer. So the next model will train the first aggregation layer, which will basically find the locally optimal representations from the one hop neighborhood. And then after that, we'll train another model which will have the second aggregation layer, which will find the locally optimal representations from both one and second hop neighborhoods. So the beauty of splitting GNNs in this way is that to train them in the federated learning setup, it's very easy. So what we have to do is take the first model, the server and the clients together train it, just in a typical federated learning fashion. Now this model could be anything. It could be a CNN as well, for all we know. And then you need one round of message passing after it to get representations from your neighbors. And then you train the next model by doing simple federated learning, which also has the first aggregation layer of the GNN. This model will have the information from the one hop neighborhood. And then you do one more round of message passing to get information from your two hop neighborhood. And then you do the further training. So you can keep doing this as many times as you want, depending on how many depending on how much information you want from the graph. So this makes it very much deployable in practice, even on asynchronous networks, because you can independently do federated learning and message passing. So our evaluation goals are pretty simple. We want to take the node classification task and see how RETEXO GNNs perform versus GNNs, because it's a slightly different objective, right? GNNs is global object, like GNNs have a different optimizer and RETEXO GNNs have a different optimizer. We want to see how it performs in real world tasks. And then we also want to measure the communication efficiency, RETEXO GNNs versus GNNs. And finally, you want to see how feasible it is to deploy RETEXO GNNs in federated learning frameworks. So we evaluate RETEXO GNNs in semi-supervised node classification task over several data sets using popular GNN models and even using early stopping as well. And these are the results for node classification versus communication efficiency for a few popular data sets. So on the y-axis, you have accuracy, and on the x-axis, you have communication on log scale. And you can see that RETEXO reduces the communication by a lot. So it could be even an order of magnitude higher. And the accuracy loss is pretty, like it's very small. It's 2% on average across all settings. And more importantly, RETEXO GNNs are actually deployable on typical federated learning frameworks, which means like you can train GNNs on fully distributed graphs. So for this, we use Flour to show this. We use Flour. So we can't do a fully distributed setup simulation because for that we need a lot of equipment. So instead, what we do is we just take a data set, we split it in half among two Raspberry Pis, and then we implement a client-to-client communication channel on top of Flour using Flour and Blue Dot. It's a different library. And this communication channel is on top of Bluetooth. We choose Bluetooth because we also wanted to simulate asynchronicity in communication. And we have a Flour server, and Flour server code is already there. And the communication between the server and client is pretty simple, and it's already there in the library. So we measure the actual performance of training simple RETEXO GCN. We find that all the performance, like it can be deployed on small devices as well. So for instance, it just takes 584 MB per client on communication channels, and then client to client communication also, it's just 0.08 MB per message passing around. And in total, it takes about 570 seconds to do the federated learning with except for we don't include the time when the clients are not in proximity, so they can't share data when they're not in proximity, right? And each client-to-client communication round takes about 63 seconds, but that's only because both of these clients are storing large subgraphs, and they have to share a lot of data. Now, we also assess how it would turn out, how scalable it would be if it was a fully distributed setup. In a fully distributed setup, this would be even more scalable and would require much lesser resources, because there'll be just one node per client, and one node requires much lesser data to train, and the only size requirement is the model size. And also the client-to-client communication would involve very little data to be shared. For instance, if there's in a fully distributed setup, two clients would require only 0.6 seconds to share data between them on client-to-client communication channels, and require much lesser RAM. So in conclusion, we studied this very important problem of federated graph learning, and we show that we argue that GNNs are impractical to train as is in such setups, and we give a novel framework called RETEXO, which transforms GNNs into RETEXO GNNs, which are practical and efficient to train on distributed graphs. RETEXO GNNs can be trained even on mobile and asynchronous environments. And finally, we demonstrate it with integrating it with Flower by extending its code base very minimally, actually. Yeah, that's it. So the code is not public yet, but the paper is. And I can show you the code. We have Dockerized everything, and we have the code ready to be integrated with Flower, but I guess we can talk about it later.
Great. Thank you so much for the talk. It's really cool stuff. And I think it's pretty original too. I haven't seen, just like the first talk, both things being talked about today, I hadn't seen much work at all in this space, both on the tooling side and into this on the GNN side. I can take a few questions. One question we received was, let me just look it up. One question, isn't there some leakage of information given the message passing is leaving the client? Doesn't the message encode quite a bit of data?
Yeah, it's a great question, actually. So here we don't look at how much data is being leaked in the gradients or in the message passing, but to train graphs, I mean, of course, there's leakage from the intermediate representations that is being shared between the clients. And I'd say that it's an open problem to how to avoid that, because to train graphs, you have to share something at least with your neighbors about your, to do graph learning, you have to share something with your neighbors, at least some sort of intermediate representations, otherwise it's not possible. And it's a trade-off, like how much you share would directly impact the accuracy as well. And differential privacy could, in some sense, offset it, and I can talk about it perhaps in some other, like offline or in some other presentation, but it's still a pretty much open problem.
I see that's very, very reasonable. It seems like you're taking one of the first steps to be able to make it trainable in a FL setting, but it seems like initially you've left the kind of privacy aspect of this federation, like most of the early papers.
Yeah, I just want to make sure that it's possible to train.
Yeah, got you. Oh, but one thing, the way that you answered that, it made it sound like perhaps you'd looked into the use of DP in this setting. Is that is that something you have done or in the process of doing?
So one work is something that we have already done, and it's published at CCS. So that is to preserve privacy of the edges from that are inferred from the outputs of a GNN. Now, for features, there is some work already done, and we're also looking into future works on like how to preserve the privacy of the features. Features.
Okay, I see. Great. I see also Daniel has a question. So I'll let him ask this question directly.
Yeah, thank you very much for the presentation. Yeah, I want to know how RETEXO works under a sparse distributed graph. Like, what I mean, if the performance is expected to be good or it needs to be somehow, let's say, fixed.
Sparse graphs, I mean, we have measured the performance over sparse. Actually, all of the graphs that we've considered are sort of sparse itself. I mean, they don't have too many edges. And in fact, sparse graphs are probably even better for communication because you don't have to like communicate with a lot of neighbors. But node classification accuracy wise, if GNNs work on such graphs, I think RETEXO GNNs with a very high chance are going to work on that graph as well.
I see. Good, good. Well, we're getting a bit low on time and so on. So I think we'll cut the questions off here. But again, thank you for the great talk. It's really interesting to see someone working on this intersection of FL and GNNs, given that GNNs are such an exciting area in of themselves.